Hello, in this video I will be talking about the MicroBooNE paper I mentioned seeing in the news last time. It excludes the possibility of a fourth sterile neutrino being the explanation for some anomalies observed in earlier experiments. And this video will follow sort of the physics recap format from my previous video, or like the previous big video, not the previous video on the Nobel Prize. So what does all this mean? Well, neutrinos are very light particles that, for now, correspond one-to-one to the leptons, those being the electron, muon, and tau. Hence, electron, muon, and tau neutrinos. This electron, muon, tau thing is called flavor, and this flavor can change or oscillate depending on how far the neutrino has went. The interesting thing about this is for this to be theoretically possible, the neutrino must have some non-zero mass, which is in conflict with the current standard model. That said, these oscillations have been observed before. In fact, since we're on the topic of Nobel Prizes anyways, the observations which have proved that neutrino oscillation can in fact occur actually won the 2015 Nobel Prize in Physics, which means a modification to the standard model will be necessary to fully explain these observations. So this paper by the MicroBooNE collaboration provides a further step to improve, or rather perhaps constrain, the improvements which need to be made to the standard model by effectively disproving the existence of a fourth sterile neutrino. It is sterile because it cannot interact with the weak force in the current model, at least, and I will discuss in more depth why this is later. But before that, I would like to talk a little bit about the experimental setup. Now, I did look into this outside the paper itself, and while I won't go too deep into this because I'm not an engineering kid and do not plan to be, I do encourage you to take a look at the nearly 100-page long document concerning the design and construction specification for MicroBooNE. It will be linked in the description. It's not open access, but you might be able to get your hands on it through your institution. It's not happening, is it? But yeah, I've linked it in the description. You should read it. It's cool, and I'm also not going through this alone. So what MicroBooNE actually is this liquid argon time projection chamber. A liquid argon is a liquid, a very cold liquid specifically, that doesn't really interact with much, considering it's, well, you can't call it a noble gas, can you? Yeah, from what I can tell, the reason liquid argon is used is for it to be easier to get the electrons from the ionized atoms of argon to the wires that actually do all the detecting. And yeah, these are the wires that actually do all the detecting. This movement is facilitated by a strong electric field in the time projection chamber. Of course, to keep the argon at as a liquid, the chamber must be really cold. How? Well, a ton of energy and a ton of foam, as you can see in this picture right here, basically creating a giant thermos. Right. As for why it's called a time projection chamber, which I have totally not been reading as time protection chamber the entire time I was researching this, because I'm illiterate, it's because the electrons inside it drift from one side with all the wires, drift from one side, um, or like where the incoming neutrino came from, to the side that detects them, right? And in order for this to be possible, the electric field must be calibrated really precisely, or else the actual time projecting or figuring out where something was before it was detected would be basically impossible without that, right? So entering the chamber are two beams, as pictured here, obviously not to scale, which is what makes MicroBooNE special and particularly fit for this experiment. Because there are two effects that counteract each other in all other single beam experiments. That of electron neutrino appearance and the gallium anomaly, which we will also get to. Neutrino or electron neutrino appearance is the fact that muon neutrinos have been observed to oscillate to or become electron neutrinos sooner or at smaller distances than expected, than previously predicted by the theory. The gallium anomaly, however, is the complete opposite. It is the observation that there are less electron neutrinos than expected, and this is also referred to in the paper as electron neutrino disappearance, right? And so without having these two beams, these effects would basically cancel each other out and make it much harder to detect any contributions that a sterile neutrino might have. But having two beams with two different compositions, uh, as you will see here, with two different compositions, basically removes this so-called degeneracy. Just from the data, from what I can tell, there doesn't seem to be like any physical interaction between these two beams, and this breaking of the degeneracy is also shown in the two panels of Figure 1 from the paper, right? As mentioned in the note to this figure, these two graphs actually show just like an expected number of hits or detections, which means nothing is being argued yet. That is crucial to understanding this correctly, okay? So this will be on the test, remember that. Yeah. So what these graphs actually show is the expected number of hits or detections of anomalous events, such as electron neutrino appearance or disappearance, depending on, roughly speaking, what the mass of the fourth sterile neutrino would be. It's actually a bit more complicated and involves so-called mixing angles, but that will be discussed a little bit later. So how are these neutrinos, how these neutrinos are generated is also quite interesting. In the booster neutrino beam called the BNB in the paper, they come from pion decays. These are mesons that consist of an up quark and an anti-down quark, or a down quark and an anti-up quark. And no, those things aren't the same because particle physics is like that. The opposite of down isn't up, I'm sorry. Either way, they decay into a muon neutrino and an anti-muon, as seen here. These pions can also decay into electron neutrinos, though this is very rare, hence why there's a much smaller fraction of electron neutrinos in this beam compared to the other one, the neutrino main injector, or NUMI. Remember this, it will also be on the test. As for the NUMI beam, it comes from a mixture of pion and kaon decays. Kaons are interesting because they can actually also decay into pions, and this happens relatively frequently, actually, around 50% of the time, if my memory is not failing me, because I stupidly forgot to put this in the script. Yeah, but they can also decay into the above-mentioned muon neutrino and anti-muon pair, as well as this decay chain, right? A pion into a neutral pion with a positron and a electron neutrino, as well as this next one, a negative kaon into a neutral pion, plus an electron and an anti-electron neutrino, or an electron anti-neutrino, I think. So these decays, even though they only happen around 5% of the time, they're still much more common than the 0.1 figure. And I actually don't know how to precisely quote this figure as, because this is from the Wikipedia page. on these decays, but the paper quotes something like 0.57 electron flavor content, but this is most definitely just because of some experimental thing I'm not aware of. I trust both sources equally. I just don't understand enough about this to reconcile them myself. So the second important key point to understanding where we're going with any of this is neutrino oscillation itself. I have found a very helpful visualization for this phenomenon that I also linked in the description. So as for what it actually is, well, I have mentioned previously that neutrinos have some non-zero mass, or they must have some non-zero mass, and specifically they have three mass eigenstates, or three masses which they could physically be. Now you may hear three and think that corresponds to the flavors, just how electrons are lighter than muons, which are in turn lighter than tauons. And while this is mostly true, it's actually a bit more complicated, and how the masses and other properties of each flavor connect are actually governed by mixing angles. These are also talked about in the paper, primarily in the equations that govern the probability that the muon neutrino to electron neutrino flavor change will occur. But these angles really aren't anything to fear, and you don't really need to know them, like, really need to know why they're called angles if you don't need the maths aspect of this. But you can look into the Wikipedia page, like, it has everything. Honestly, that's where I get all my information from. Well, not all my information from, but like the starting point for the things that I don't need to go too in depth into or be like too sure, right? Like I'm just giving a surface level explanation here. But yeah, all they are is a description of the probability that a specific flavor will have a certain mass. It is also important then to clarify what distinguishes different flavors, if not their mass, and that would be their decay. Like tau neutrinos, for example, decay into muon and electron neutrinos, but the reverse cannot happen. An electron neutrino cannot decay into a tau neutrino. But as we will see in the discussion on Z-boson decays, to some extent, this is also related to mass. So yeah, it's like a whole web, really. So uh, these uh, these masses, and let me actually try to draw something for you here. Get some axes. Hello. Okay, I guess. Okay, I guess we just start drawing then. All right. This will be like the distance, and this will be distance d, and this will be the probability p, right? Let's just say, and I will denote, say, electron neutrinos with this yellow right here, if I can figure out what I'm doing. So like, let's say that this is the probability that the neutrino will be in an electron flavor state, right? Going to be using this purple to denote the muons, right? And in reality, this will have this won't be like this perfect, right? There will be a lot of cool different shapes that we will see at the end of the video when I go to play around with that visualization thingy. But to give you the basic idea of like propagation, this is like basically what happens. And the tau is a little bit less is little bit less likely, so I'm drawing it at the bottom here, but it is much heavier, which is why the wavelength is much larger, right? So this is roughly what happens, right? This means that at different points, the neutrino will be more likely to have different masses. And of course, even when the probability that it is a tauon is really low right here, it's still not zero, right? Or a tau neutrino, I apologize. And the flavor, right? I know I have been like referring to these as flavors, but again, mixing angles, the probability that say when it has an electron neutrino's mass, it will also have the electron neutrino's flavor is governed by the mixing angles, right? So let me just erase this really quickly. So what happened and what has been observed at experiments such as MiniBooNE, not MicroBooNE. MicroBooNE exists to try to explain these anomalies. MiniBooNE is the place or one of the places where they were detected at first, is that the actual length that the neutrino has to travel before its flavor oscillates is much shorter than what is predicted by the model. And one of the theories to explain this has been that there is a fourth possible mass eigenstate that has a smaller difference with, say, the electron neutrino than the muon neutrino has, right? And the reason we've not detected this one directly is actually quite convenient, as you will see in the discussion on Z bosons later. It's that it literally does not interact with the ways we've conventionally measured neutrinos. It's a so-called sterile neutrino, right? It does not interact with the weak force. So let's get to the Z boson, which I have been vaguing this entire time. The Z boson decays into particle-antiparticle pairs, and the reason it cannot decay into this potential fourth neutrino state, or really anything more than we already know it to, is not because of spin or anything, because the Z boson is the most neutral boson you could have. It has no charge, it has nothing really. It has no spin from what I can remember. No, it does have spin. But yeah, it's really neutral, which is why it decays into particle-antiparticle pairs, right? Um, so the reason it cannot decay into this new mass eigenstate is not because of spin or anything else not completely neutral about the Z boson, but because of decay width. I know I mentioned it in the context of lighter things not being able to decay into heavier things, but perhaps that's a bit misleading since this paper actually talks about like light sterile neutrinos, which would not be affected by this from what I can tell. The reason I brought that up is actually because of basically just a fun fact that Z bosons can't decay into a top anti-top pair, right, as seen right here. Right, the hadrons up-type quarks except the top quark. Because right, because they don't have the mass to be able to decay into that pair. They don't have enough mass for that, right? And as for what the decay width is, well, that's a little bit more complicated. Actually, let's stay on the slide. From what I understand, it represents all the possible decays summed together, or more precisely, the sum of some constants that govern the rates at which different decays proceed. It is also related to the uncertainty in the energy of the particles, such as the Z boson, that decay very quickly, right? Right here, right? The energy, or well, basically the energy, or the uncertainty in the energy is equal to the decay width over 2. It's pretty neat. So this means, so we have been able to measure this decay width really precisely, and it basically just can't fit another neutrino or another anything really. And we have measured it in experiments such as Aleph at CERN. And as is implied in the paper, I'm expanding a bit here. The fact that these theoretical predictions for the possible decay of the Z boson or Z boson, so the something, corresponds so well with these experimental measurements related to the uncertainty that they can only be the terms that we already know of, which means the Z boson cannot decay into the sterile neutrino, or really the sterile neutrino-antineutrino pair, but you get the point. And I personally find this confusing because, again, the Z boson is its own antiparticle. Um, so if it were to decay into a sterile neutrino-antineutrino pair, then no conservation laws would be violated, especially considering that sterile neutrinos are also predicted to interact with the Z boson, which is crucial to my confusion, but sure. Even though the Z boson is technically part of the weak force, when it said something specifically the sterile neutrinos don't interact with the weak force, it's meant that they don't interact with the W bosons. As for why that is, um, it seems to have something to do with the actual group theory representation. So left-handed particles form so-called doublets. For example, left-handed neutrinos form doublets with left-handed electron neutrinos, causing these neutrinos to behave like electrons in weak interactions. It is important to note the weak isospin determining whether a particle interacts with the W boson for electrons is positive 1/2, while for electron neutrinos, it's negative 1/2. However, right-handed particles, the sterile neutrinos in this case, do not form such doublets due to there being no equivalent electron to pair with. Hence, to quote unquote like keep the balance, the right-handed sterile neutrino would have to have a weak isospin of 0, right? And this took me an embarrassing amount of time to figure out, but I'm glad that I did. Thank you, Wikipedia. And there's a heart emoji in my script here, so that's neat. This might be the wrong presentation, because I still have graphs to get into, but that's okay because I can just screen share. Let me turn on the light actually. I can just screen share my browser if you give me a little bit of time to set it up. All right, we are back in business. So yes, believe it or not, we're only now getting to the graphs because I actually had time to research this. All right, so the figure 2 graphs, yep, these ones, show the observed number of electron neutrino detection events at each energy level. And they look scary, right? They look exciting because there's these like huge dips and huge overshoots, and it looks like something is happening, right? That we need to look at and develop something new. But from what I can tell, this isn't really anything new, right? These are just the same electron neutrino appearance and disappearance results observed in other experiments. In the text preceding this figure, which I can actually show this time, as you can see here, um, right, a fit for the mixing angle, which once again would be related to the sterile neutrino's mass, was derived. So really this seems like figure 1 all over again, but with concrete values for the mixing angles instead of a range being shown, right? In the figure 1 graphs, there was a bunch of different ones depending on the mixing angle. Right. So it doesn't really do anything in itself to prove or disprove the sterile neutrino hypothesis. It's basically a mathematical fit, if anything, and though this is just at a glance. These jumps and dips outside of what the sterile hypothesis would predict would make me want to look further into this hypothesis because looks like it doesn't really match our data. And figure 3 does exactly that, right? It looks further into this hypothesis. And in fact, I'd consider it the real smoking gun of this paper, which shows that the kinds of parameters which would be able to explain previous experimental results are actually excluded by the MicroBooNE result, right? This is the data and everything that like the data cannot explain is excluded, and everything that is excluded is the previous data. Wow. So it's really important not to confuse MicroBooNE with MiniBooNE here once again, because that made me bang my head against the wall a little bit. But I am illiterate, so you gotta cut me some slack because winners can't be choosers. So the y-axis of this parameter space is the difference in the mass of the electron neutrino and the sterile neutrino, while the x-axis is the sine squared of the mixing angle, specifically between the muon and the electron neutrino, right? And it's actually the mass squared, but that's basically just a numerical difference. Although this mass is in itself related to the mixing angle involving the sterile neutrino through some maths, the important thing to know is that this panel is about electron neutrino appearance, right? So it's about when muon neutrinos become electron neutrinos. Because that's what the MiniBooNE experiment was about, right? It found more electron neutrinos than predicted, and this mixing angle of muon to electron neutrinos governs that oscillation. So how likely it would be that a muon neutrino would become an electron neutrino and then explain this anomaly, right? And the second panel here compares the electron neutrino to electron neutrino mixing angle. Basically, the probability that the electron neutrino doesn't decay. Please don't take a shot every time I say electron neutrino in this video because I cannot pay your medical bills. And this also excludes almost all, but very important to note, not all possible combinations of parameters for this singular sterile neutrino. Though I don't know how much these tiny areas really help, considering all of this was just plain excluded. So, you win some, you lose some, really. And I really want to dwell on these graphs, even if I don't have a lot to say. I mean, the graphs really speak for themselves unless you want me to go into the statistics of it, which I will not do. Statistics scare me, so I'm just going to leave this here for a minute, like as a moment of silence for all the sterile neutrino parameters which have been excluded by this paper. Perhaps. All right. So I also wanted to mention a graph from the extended figures, actually. I'm going to try to find it. Here it is. Showing various possible exclusion like contours, I guess. With the one in the previous figure being this data current result line, the solid red line. And whoever chose these colors passion was clearly graphic design, as you can see here. So this is also pretty cool, right? Like we're seeing the evolution of the detection technologies in a way, right? This is only the NUMI. And this is the 2023 result, which, as you can see, had these like weird little zigzags, while the current data is more or less smooth. That's pretty nice. And then the median sensitivity as well. And there's also this graph from also this graph comparing the electron neutrino disappearance, right? This was muon to electron, and this was electron to electron. So a bunch of statistical stuff, and this is the contour we have now. It's like actually so interesting to see that this bump right here is almost in the opposite direction of this dip to the NUMI only data. But yeah, that's pretty neat after all. So let me go back to the presentation now to answer some final questions. So why this paper, right? We're doing the format again. Why I chose to cover this paper actually should be pretty obvious. It's firmly in the niche that I want to go into the future, namely particle physics, developing physics outside of the standard model, etc. And I feel like once you get a grasp on the basic concept of neutrino oscillation, it should be pretty easy to understand the conclusions drawn. And this really seems like the kind of research which would open tons of doors for the future, and hopefully I get to follow that in these videos. Specifically, and this is kind of further research questions already, this paper pretty clearly states the future vectors of research. It's possible the anomalies could be explained by more than one sterile neutrino or sterile neutrino decay effects, on which papers have already been published and work is being done. It also highlights potential new particles in the dark sector, so dark matter related stuff. And as I mentioned earlier, technically, not all parameters have been excluded as well. In fact, something interesting that you may not have gleaned just from reading this paper is that sterile neutrinos are actually a potential candidate for dark matter, among other things, of course. So it's not like this paper like completely upends any theories we may have about dark matter, but it is important to note nonetheless. The reason sterile neutrinos have been so hard to detect in context of dark matter is because they do not interact with matter at all, if only through gravity. And in a way, this paper proposed a potential solution to that problem with neutrino flavor oscillation, right? As I have already mentioned, this paper doesn't appear to outright disprove the existence of sterile neutrinos. It only disproves the existence of only one additional sterile neutrino, right? I mean, of course, make no mistake, this is a null result, right? We didn't find the sterile neutrino, but it opens a lot of like possible other explanations because this was basically the leading theory, and now we have to develop new ones and test them. That's how science goes, right? I think that's what really changes about this. It's that we get to do more science, which is neat, and I am excited to see what comes out of that direction in later episodes in the future. Yeah, the future in maybe even next year. Who knows, right? So again, so thanks. So actually, you know what? Fine, we have a little bit of time. Let me fiddle around with the recording again because I wanted to do this for my own self-indulgent reasons. Be right back. All right, so this is the simulation. If you're gonna be playing around with it on your own, you don't need to touch any of the code. You can just hit run all and adjust these little things right here. So this is similar to the graph that we saw in the presentation earlier, right? But I've already just moved these around a little bit, right? If the mixing angle is smaller, then there's more overlap. Up to a point. It really is around the sweet spot right here, apparently. Again, I don't know what I'm talking about. I'm just playing with this like toys. That's pretty neat. Seems to like have a huge jump right here. Around 1.20. Okay, let's see if we can get this to go back. Let me zoom out a little bit further. What is the mass squared gap? Okay, it apparently just what does energy do? Ooh, wow. Okay. Oh, that's pretty neat. This is probably just some kind of code artifact with how it's being calculated. I don't think it's actually spiky. It's pretty neat. I don't think I can get the precision I want in here. Hold on. Let's do like 40. Okay, it does exactly what I expected it to. This section might not be really interesting. But you know what will be? This section. Because it includes all three flavors. Wow. Yeah, my visualization wasn't like perfect, but I'm gonna fix that now by showing y'all this one. So once again, we have the mixing angles. I might need to zoom out even further. 6, 7. Can y'all see that? Or is it behind my like zoom controls? 6, 7. I need to grow up. I actually need to grow up. All right. Wow. Okay, so between 1 and 2, I think okay, I think 1 and 2 might be the muon and tau, maybe. It doesn't really do much of anything. No, no, it's definitely muon and electron. Yeah, because the tau doesn't really get changed much, but the muon electron. Okay, so I'm glad I didn't lie throughout this whole video because re-recording that would be a pain. Oh, okay. Wow, that's a lot. Hey, it's Christmas colors. I wonder if we crank this. Okay, no. I wanted to get like all Christmas colors and for the tau to like not even exist. But I don't think I'm gonna be able to do that. Um, yeah, because the muon is kind of in between. Wait, hold on. Okay, I think we can hit a sweet spot. This is like kind of like playing like with a low frequency oscillator, if you know what that is. Okay, okay, hold on. Let me cook. Wait. Hold on. I think if we get this, no, no. Okay, I think this might be the closest we're gonna get. This is fun though. I like pretty pictures. I like when science makes pretty pictures. Yeah, we're getting close. Um, we just like turn these parameters around. Up and up. Okay, this isn't working. Um, First one in the comments to be able to choose the parameters to make it like all red and green, if that's even possible. I'm frankly still not 100% sure that's possible with like the blue line at the very bottom gets a cookie, a fictional cookie that I'm not actually gonna give you, but you can say you are proud of it. I don't know. So cool. I love I love quantum mechanics. Okay, there we go. We got okay, I think I'm just gonna leave it like this so it's like okay to look at. Okay, charge parity violating phase. Okay, it just moves them around. It's just a phase. I don't know what I expected. Large mass squared gap. That's the mass difference we were talking about. Okay. Yep, the energy still does the same thing it used to. Wow. Christmas light. Wait, I wonder if we can get the green all the way so that it looks like a Christmas tree. Hold on. Sorry, I'm not doing anything for the holidays, so I'm just oh, you know what? I'm taking this. Cookie offer has been revoked. I'm taking this. This is so cute. It's Christmas in the village, and then there's Aurora, and then there's like Northern Lights. This is so cute. Oh my gosh. I'm saving this. Hold on. Screenshotting this. Are you kidding me? This is so cute. All right. Hold on. What was I doing? Oh yeah, we were trying to get green at the bottom. Green is this one. Wow. And then let's get this. Whoa, this is so cool. Okay, we're kind of doing something. Let me just get this energy a little bit higher so it's not painful to look at. Okay, maybe we can. It's fine. It's fine. It's fine. Who's still watching anyways? Okay, we're closer. We're closer. Hold on. Let me cook. Oh, whoa, whoa. Wait, what? Oh, because the mixing angles are the same. That's so interesting. Sorry, I'm yapping. I'm like actually yapping. Aw, where did it go? Oh, come on. Okay, we're separating it somehow. Oh, wait, I'm stupid. Yeah, there we go. So, wait, now we actually might be able to do it, to do the original thing I wanted to. Okay, this is close enough. If we turn this initially to muon. No, okay. Talon. Wait, I'm stupid. The electron is the green one. I was going off my own like personal interpretation that the Talon has to be green. I don't know why I thought that actually. Oh, that's so cool. Okay, we're getting somewhere. Okay, I think if it is originally okay, we already played it. Aww. Oh, look, you can see that the probability that like the top of the probability that it becomes a tauon increases when you change the initial flavor from a muon to an electron, from an electron to a muon. Look, that's because the muon is heavier, I think. I think. Don't quote me on that. It might be something with these mixing angles. I don't know. It's probably something with these mixing angles, actually. Yeah, it probably is. Um, this is so cute. Oh, this is so pretty. Oh my gosh. Wait, this is actually so pretty. I'm stealing this. Are you kidding me? I'm screenshotting this. What? Look at that ombre effect. This is so cool. Okay, that's it. That's it. The video's done. I'm ending it on that. I forgot that I put my controls. All right, thank you. Bye. See you in the next one. The next one's gonna be on OpenAlex. The statistics I sourced from OpenAlex. Don't worry, they're not gonna be as scary as the statistics in the MicroBooNE paper. All right, see you there.